with x1, x2, because alpha, you know, is entering into x1, and beta is entering into x2. Okay. So if you want to solve for that, I leave it to you. Okay. So what I did here is that I consider that as if uncorrelated, which I forgot to mention. Okay. So, but you know, since they're not uncorrelated, so I mean, in principle, I should take into account alpha and beta. So a very efficient way is to look at the block diagram, and then I leave it to you. So if I look at the block diagram, I have alpha n, okay, which is entering into a filter, okay, which is a 0. So I have 1 minus 1 plus is equal to minus 1 minus 1 half. So 1 plus 1 half z to the minus 1 minus 1 half z to the minus 2. Okay. Now this one is generating x to n. Then I have a beta n, which is entering into a pole. It is 1 minus 1 half z to the minus 1. This generated, no, that one is generating x1, and that one is generating x2. Now looking at the formula, it is x1 plus x2 minus x3, and x3 was alpha plus beta. So you know, then x3 is summing with alpha plus beta. So you know, I have alpha, beta, that are summing. Okay. Here I have alpha plus beta. Okay. And then if I look at the formula says now subtract minus alpha plus beta. And this makes a yn. Okay. So, which means, since I have alpha plus beta, means that, this is now the elaboration for that, that means that it is like if I am removing alpha and beta. So I'm messing up, so let's make them. I want to do the other exercise, and then you know I'm messing up. Okay, so I'm removing alpha, and I am removing beta. This one is yn, okay? So, you know, that means that I have in parallel, so it looks like, you know, if I am removing alpha from here, so I'm removing alpha from here, okay, minus, and I'm removing beta from there. If you write the formula, it comes to the same. Now we leave it to you. So we compute now the autocorrelation using these formulas. Okay. Compute by yourself. Considering that yn is equal to x1n minus alpha m, and this is one new variable, plus x2n minus beta. So you can call it x1 tilde. You can call it this one x2 tilde, and then you can recalculate everything. x1 is easy, x2 is a little bit more complicated. So you have it. So you have it. You go there, you have it. Okay? Let me move on to the next exercise. Now, the next exercise is part of an exercise which is bigger. So this is an exercise number 5, which is on autoregressive moving average spectral analysis, which is too early for you. But you know, any exercise in the exam, it will contain the computation of the autocorrelation. So this is a piece of a big exam, and this is on the exercise number 5. So that means that you need to know how to calculate the autocorrelation of a random process analytically, in any case. Now, let's look at it. So, let's look at it first. So, alpha and beta are white, okay? So alpha, you know, as a power 1, and beta as a power 5. They are statistically independent random processes. These are filtered in a slightly different way as before. So, now y1, what is y1? y1 is 1 alpha, y1 minus 1 plus alpha. Okay, now, that one is same as previous exercise. Okay, this one is an autoregressive order 1. Okay, now, what is y2? y2 is the same as, you know, the previous exercise, except that I have beta n minus 2, beta n plus 2. Now, this is a moving average, okay, but you know, we need to calculate that. Okay, so let's make it. So let's compute the z-transform on the fly. Now, if I need to compute the z-transform on the fly, this is y2z is equal to, that one is z to the power 2 plus 1 plus z to the minus 2 to the power everything multiplied by the z-transform of b, which is bz of the sequence. Now, what moving average is this? I have z to the power 2 plus 1 plus z to the power minus 2. So the sequence is 3 samples, right?
5 samples.
5 samples. Because it's, okay, so I can collect z to the power 2, and this makes 1 plus z to the minus 1 plus z to the minus 4. Okay? So it is a sequence in total of 5 samples. 1, 0. I have the 1 in position 2. And 1 in position 4. So the difficulty of this exercise, now, given that, is the same as before. Okay? So this one, what order is this? The order is MA4. Now what I'm doing here is calculate x. Okay, calculate x. Now x is y1 plus y2. Now, y1 is autoregressive order 1. y2 is moving average order 4. So what kind of process is this? It's an ARMA. Okay? So we understood the trick. It is ARMA. And it is ARMA, okay, which has, you know, it has the autoregressive component is 1, and the moving average is 4 plus 1, so it's 5. Because there is a roots that denominator that moves in the numerator. Okay, that's it. Now, what I'm asking, I might ask, which is totally destroying your capability to illustrate the power spectral density. This is what I want to show you now. Illustrate the power spectral density of Y1 and Y2. Okay. So, how can I calculate the power spectral density? So my goal is not to solve exercise A1, it's not to solve the exercise A2, which is the same as before, simply, changing the polynomial with the zeros. But my goal is to sketch the power spectral density for Y1 and Y2. This is my goal, okay? So how do I make it? So, in order to make it, I need to calculate the position of the poles. And I need to calculate the position of the zeros. Okay, so let's make it. So the outer regressive order 1 is of the, it's by filtering with 1 minus 1 half z to the minus 1. Okay? So my goal is to sketch for power spectral density. Now here the input is, let me see, the input is alpha with the power 1. Okay, so alpha n, here it is y1 n, the power sigma square alpha is equal to 1. So for power spectral density, the power spectral density is, so it is power spectral density y1 omega, okay, it is the z transform of the autocorrelation sequence computed for a long circle. Okay? So I use the definition. So it is the power spectral density, so it's a z transform of the autocorrelation. Now it is sigma square alpha, then it is 1 minus 1 half z to the minus 1 times 1 minus 1 half z. Calculated for z equal aj j, okay, along a circle. So that means that I need to face where is the singularity. So that means in the z transform, I have the leading pole is here in 1 half, and I have another pole here in 2. So, if I want to get the power spectral density, that means that this is the real part of Z, this is the imaginary part of Z. So what I need to calculate by moving along a circle. Okay, so this is omega. I need to calculate the Fourier transform by walking along the circle. Okay. Now, what I'm asking you is to make it graphical. And so, in order to make it graphically, I need to calculate this distance multiplied by that distance. So the distance that I need to calculate is this one. I use the color pinky. Okay, so it's this one. So if this one is a point A, this one is a point B, this one is a point C. So now that means that the power spectral density is SY1 in omega. It is equal to sigma square alpha. Then it is AB, the length of AB time the length of AC. So you know, I'm not asking you to be very precise. Okay, it's not required. But you know, I mean, you can sketch approximately. So let me say another word. Point the length between AB is equal to the length of AC. So that means that this one is equal to sigma squared alpha squared. Now, look at the book. So that is AB squared. So the length to the square. Now, this is the geometrical part. So what I'm asking here is to sketch the power spectral density. So since when A, so the point A, when A is here, the length is minimum, and then because the length is minimum, the amplitude is maximum. So that means that if omega, so this is the omega axis, when the omega is in 0, the distance between this point and that one is, so that one is 1/2, the other is 1/2. Okay? So then you know the distance is 1/4. Okay? So this point approximately is 1 divided by 1/4. Okay, so it's 4. Let me sketch that. When omega is 0. When omega goes on the other side, the length is 1 plus 1/2, which is 3 divided by 2, to the power of 2, which means 9 divided by 2, which is to the is the denominator, so is 4 divided by 9. So in pi and minus pi, here is, am I right? It's 3 to 4, 9. Okay, and the same here. So the behavior, you know, is approximately this way.
Sorry, I didn't understand how we find the omega. How is it moving along the circle?
I mean, this is the omega. Okay, so this angle, let's say, this angle here is representative z of z equal aj omega. So it means the radius is 1 and the phase is omega. Okay? So that position here as the angle, this angle is omega. So when I change omega, you know, when I walk here, which means my phase is omega, then I'm exploring all the circle. Okay? Then, you know, let's put myself here, sitting there. Then I calculate the distance from here and from there.
Okay, it's always related to C, the point C, the distance.
Yeah, I'm reading it out. So it is 1/2 multiplied by aj there. Okay. So that one is really okay. If you like this way, make this way. That one is. So it is 1 divided by 1 minus. It is 1/2, then it is aj0, which is 1. Okay? So that one is 1/2. Then you make the other. The other is 1 minus 1/2, then it is aj0, which is 1. Okay? So that one is 1/2 to the square. Okay? This is for omega equals 0. Then I keep moving. Okay? So when, I don't know, when, I mean, the other point, which is easy to be computed, okay, is when it's pi. And pi means it's there. Oh, so when omega is equal pi, that means that, you know, on the circle, okay, I have these roots, and the distance is here. So the distance from here to there is, this is 1/2. So it is 1 plus 1/2. So it is 3 half. Okay? So that one for omega equal pi. So then, you know, the distance is 3 divided by 2, which is a square, which is 9 divided by 4. So it is, you know, it is 1 divided by 9 divided by 4, which makes a 4 divided by 9. And this is the value at the point omega, omega equal pi. Okay, so that's what I did. Okay, so usually, you know, what you do, you compute some of the points where it's easy to compute, just to have an idea. And for the telecom, okay, you're not telecom, right?
No.
Okay, so for the telecom, I mean, usually the telecom, they made this kind of sketch by hand many times, okay? I'm not asking you that. But, you know, I'm asking you to make a sketch of the major, the most important, okay? So, and then you know that every time you have a pole, you have a kind of resonance. And so since you have a resonance, then, you know, your power spectral density is getting a spike. I mean, similar, big amplitude, okay? So it goes on to the denominator. So just to explain you a few words, okay? So usually, you know, the telecom, they make by hand. So when they see a set of pole and zero, I mean, immediately they figure out how is the power spectral density, or at least, you know, the behavior in the Fourier transform. So let me make just a quicker review on that. So imagine that you have a set of, I don't know, you have a pole here, just to make it simple, okay? A pole here, and a zero there, and we have another pole here, okay? So if you are like in this position, so your Fourier transform, okay, is, or your spectral density, you know, you simply make the square, okay, is computed by, now we call this point is A0, and then I add B, C, and D, okay? That's another example, huh? Okay. Now this one is a 0, this is a pole. So, you know, what I compute this distance, okay? Then I compute the other distance, then I compute these elements. So my power spectral density in this case would be squares, no, I have all the zeros. So the zeros are A0, B, the distance to the square. Okay, because it's a 0. For the pole, goes on the denominator, okay? So for the pole, I have A0 going to B, distance to the square, and then I have A0 going to C, to the square. Okay, so in this way, you know, I compute the power spectral density in omega equals 0. Then, for instance, if I look at this point, you know, in this point, let's consider A1. Now, A1 is very close to C. So since A1 is very close, for this case here, so I have A1B distance, then I have A1B, okay? Then I have A1C squared. Now, A1C is very small. Imagine this pole is very, very close to the radius, to the unit circle. Okay. So what's happening? This one is very, very small. Since this one is very small, that the reciprocal gets very big. So if I need to sketch the behavior in this case, I expect that since here B is very close and C is very close as well, so I get two resonances. Okay? So, you know, in my power spectral density, okay, now this is 0, so what I expect that, you know, I have a moderate resonance in B, then I have a big resonance in C, and then, you know, when, I mean, since the distance here in D, imagine now D that is a 0, which is very close to the circle. Then you know in this case, when I am in pi, it is a shrink to 0, or very small. So the behavior that I expect is this, then you know, with the appropriate symmetry. Approximate, okay? So here, you know, is in 0. This is in, I don't know, 40 in pi divided by 4. Okay, it's not in wood scale, but you know, this is just to give you an idea. So usually, when you have a pole, if any pole represents a resonance in the system. You know what the resonance is? Okay, what's the background? I don't know. Okay, so this is like a resonance. So if you have a resonance circuit, you know, it's okay. That's the same. So it's a, I mean, this is a kind of numerical resonance because it's for numerical system. So you have a resonance, so I have a resonance here, which is very close. But you know, the closer it is to the circle, the smaller is the star, the bigger is the amplitude. And virtually, when the pole goes into the circle, then you know my amplitude is going to infinity. Okay? So this is just to give you an idea. Okay? So that means that every time I see a pole, which means in our case, every time I see an autoregressive process, I might spot where is the resonance, which means where is the pole. Okay? So when I talk about resonance, I talk about what is the angular frequency corresponding to the pole. And that angular frequency is representative of the resonance of the system. Okay? So for the same, you know, now what I'm doing is I have a sequence, these is a sequence, okay, which is z to the minus 2, z to the minus 4. Now, I don't see the property for that. Right? You know, actually, I mean, I can calculate, so I mean, what you are allowed to do in during the exam, you take these 5-point sequence, you put it to the computer, and you calculate where are the roots. That's it. Okay. So you simply you open your MATLAB, we press these 5 buttons, you calculate the roots, and then we get the roots for the system. Okay. So now, let's make, for instance, that, I don't know. So we have only roots of 0, so we have a set of zeros. Remember, the zeros are in the numerator of the system, which means that, you know, when the distance is getting closer, this one is shrinking, is putting to 0 the behavior of the power spectral density. Okay? Now, you can do yourself. Okay? Because the easy way would be to make a spectrum, or there is a filter instruction, and then you can get to the behavior of the power spectral density. But when I ask you to sketch, when I ask you here, sketch with care the power spectral density for Y1 and Y2, I'm not asking that you press the button on MATLAB. I want to see what is the rationale behind any point. Okay? And so, I mean, with the pole I did, and so you can try yourself with the zeros. Okay? I'm not doing because in principle I should now type this point, calculate the zeros, and then make the same exercise. So since we spend a little bit of time, I'm not doing it. Okay? I'm doing the next exercise. Okay? Now. Okay, so this exercise was how to compute the power spectral density analytically, or you know, by sketching.
And then this E is periodic.
We have between minus pi and pi. So it is intrinsically periodic. But we don't sketch more than minus pi. No. Okay, this one is a little bit subtle and more difficult, even if it looks as simple and the same, but it's different. Conceptually, a lot of different. Okay, now, let's look together. I mean, it is a subtle because the exercise is the following. So I have xn, look together. xn is y w w w plus 1. Okay, good. So, you know, what's happened that, you know, I have a y which is entering into the system which is manipulating w. So y is empty. Now, where is the y? How y is coming? Y, you know, is coming by an autoregressive order 1 plus z. Okay. So, you know, in this system, I can sketch the system as this way. So it is like if I have x, which is obtained by filtering w, and then, you know, using y as an additional an additive signal. So let me represent it in a slightly different way. Imagine that, you know, here I remember here there was some ambiguity because some student asked me a question and then I clarify by voice. So the system is the following, you know, so I have a Zn which is entering into an autoregressive order 1 filter, so which is 1 minus 1 half z to the minus 1. We know everything on that. And this is yn. And then, you know, what I had is that xn is by exciting. So it is, you know, let me see if it is this one or the other. This one is. They are both. Okay, so now assuming the random process is xn is equal to w blah blah blah, so plus y, and there is a filter version of the y process with an additional additive noise which is y. So y is that, and then I have a w which is a filter this is not the exercise that I was looking for. Okay, let's start with this. And then I have another, here is 1 plus z to the minus 1 minus 1 half z to the minus 2. It's not what I wanted. I choose the wrong exercise. Okay, this one is the same as the other because I'm asking you to calculate the autocorrelation of y, the calculation of x. So, you know, it's the same as the other. Now, let me modify the previous exercise and show what I want to show. Okay. So, I'm sorry. I didn't choose the. I didn't use exactly the exercise I want. Assume that, let's take the previous exercise. So we take the autoregressive order 1. So let's assume that, you know, this is a new one, new exercise, okay, which is not included there. Assume we have an alpha n, you know, and this alpha n is exciting an all zero system. So we have, I don't know, we have 1 plus z minus 1. That's it. Let's make it simple. Now the output is yn. Then we filter this by another system we call, which is 1 minus 1 half z to the minus 1. And we get xn. Okay, this is a kind of exercise that I'm asking. So, you know, this is a new example. So I have 0, 1, 0, 1 pole. Then my outcome would be a random process that is autoregressive order 1, ARMA 1, 1. Question. Compute the autocorrelation x. So calculate Rx x k. Now, if you have this kind of exercise where you have a cascade of systems, where you have a set of, you take a random process which is alpha, which has, I don't know, the power sigma square alpha, just to simplify. Then this one is filtered by a certain filter bz, and then it's filtered by 1 over az, as in this case. Now, if you are asked to calculate the autocorrelation out, don't calculate in the way it is now. Now, you will see in 1 second why. Because you know, what's happened there? If I need to calculate the autocorrelation out, my way to compute is the following. Then, you know, if I need to calculate Rxxk, this one is equal to RyYk convert by the RAAK, which is, you know, the autocorrelation of a filter where it contains poles. Now, if the autocorrelation contains poles, it's difficult to write in the closed form. And so writing this convolution is not easy to do. Now it is much more easy to use the Euler-Walker because, I mean, in principle, you should calculate the Euler-Walker here for a correlated process in. And we don't know it. So since Euler-Walker needs to have a white input, okay, white random process as an input, which means, you know, white input is just a shorthand, okay, then flip the two systems. What does it mean flip? It means that, you know, I make alpha n, which is entering into the system, which is 1 over az, which is here, it's very simple because it's 1 pole. And then it goes into cascade of a 0, which is, in this case, simple case, 1 plus e to the minus 1. Now, xn is the same. So what I did, you know, I just flipped the two systems. I just, you know, transpose pole and 0. Now, why I did it in this way? Because, you know, now I can apply the Euler-Walker in the first part. I can analytically calculate the autocorrelation in the first part. And then I can apply to the second part. So let me do analytically this part. So for this specific exercise, we computed already thousands of times, you know, the autocorrelation here. Now, why is that? This is xn, and this one is alpha. This, let me call beta n. Okay. So I indicated this intermediate output as a beta n. Now beta n is autoregressive order 1. And we can calculate the autocorrelation of beta. So now, let me do this, okay? So I copy that and I compute this. Don't worry, I'm just pasting the same formula. Okay, so this is after flipping. Okay? Now, I can compute the autocorrelation of beta. I know, by Euler-Walker, that now I can apply. Now I can apply. I can calculate R beta k, which we already computed. It's all the same. Okay, so it is it's the analytical closure form, so which is sigma square alpha. Okay, divide by 1 minus 1 half square, and then it is 1 half to the power k. This is R beta beta. So what is Rxxk? Now Rxxk is R beta beta k convolved by R b b k, which is which is obtained by the filter. Okay. Now we need to calculate RBB. So to compute RBB, I use the Z transform, and because that one is 1 plus Z to the minus 1 times 1 plus Z, because it's by definition. Okay. This one is equal to 1 plus 1, so it is 2 plus Z plus Z to the minus 1. So this sequence here, so it is R beta beta k convolved by 2 times delta k plus delta k minus 1 plus delta k plus 1. So the closure form, okay, becomes, this is just the computation. So the closure form becomes, it is R 2 times R beta beta. Okay. Then I convolve with the second one, which is plus R beta beta k minus 1 plus R beta beta k plus 1. And that's it. So we have a closure form. So remember, now, in place of R beta beta, you use that one. Okay, then you calculate that. Huh? Okay, so you have 1 minus 1 half, you group it, blah blah, you make whatever. Okay, so what to remember of that? To remember is that in case you have an ARMA, and the ARMA is a cascade, as usual, of a pole, of a zero and pole, swap it and make a pole and zero in order. Never make a zero and pole to calculate the autocorrelation, because you can do everything. The fact that you can apply the definition and then come to the end of the computation is always true, but it's a matter of time. So it might take too much time. And the more time the more increase the probability of a mistake. Okay. And I conclude this one now. I want to now to play with the method. Is it possible? Do you have some chart? Yes. Okay, excellent. If you don't mind, I apologize I don't have it. Is it okay for you using? You can stay here if you like, For my goal, okay. So what was my goal here? Okay, so I finished that one, I want to just show you a very nice way to compute the roots. Okay. So now let's invent a sequence. Okay, let's invent a sequence. Now, I don't know, since I don't want to prefer any sequence, I generate a random. Okay, I generate a random. So I generate the sequence X, I make it here. Okay, you have this menu. Yeah.
Double click.
Double?
Double click on the gray cell.
Here?
On the map window, the gray cell.
Ah, okay. So now let me, invent a sequence, and this sequence is random, unit power. How many samples? 51, 33, 100, 1,000. Okay, so we have 1,000, of samples. Okay. Now, after generating these 1,000 samples, what I want to do is to compute the roots. Okay, because that one is a polynomial. So then, I can calculate the zero, which are roots of x. So z gets a 0. Okay. So now, if I run this, okay, so now it takes a little bit. Then, I want to see where are the roots, right? Okay. Now I think that the common was a zp. Let me see. L z plot, because you can plot a 0 plot. I think it was z. No, it's z plot. You can plot a 0 and fold. I use a
Maybe it's
Z-plane.
Z-plane. Okay, Z-plane. Thanks. 0 pole plot. Z-plane. So Z, 0, P is pole. Okay, so we can see 0. So we can make it a plot of 0, and pole is 1. Polynomial. So let's see. Okay, so these are where the zeros are. Okay, so we generate it randomly. Okay, so the zeros are wherever they are. Okay, now sometimes you come and say, oh, but those zeros cannot exist outside. I say, why? Why? The zeros goes wherever they like. Okay. So, we can also zoom in to see where they are. Okay? You see they're moving back and forward around. Now, if I make the Fourier transform for that, just for you, okay? So, we will see that, they would cross back and forward. Because, the zeros means to 0. Okay? So, zeros, if I make the Fourier transform for this random sequence, it goes back and forward around 0. So let me put this one here. Okay, this is too big. So I made just a zoom. Huh? So I mean, if I make now rather than z-plane, if I make the plot of the absolute value of the FFT of x, right? X, okay. Here. You see? This is the absolute value, but you know, I use the absolute value. So that means that there is a several crossing up and down here. Okay? So I use the absolute value, but you know, I can zoom in. And then I can see that it's going up and down, but you know, between, I use the absolute value, so there might be negative value here, okay? So, let me go back here. So I calculate these set of poles of zeros. Now, let's calculate the autocorrelation numerically. It's not the autocorrelation, it's the numerical computation of the autocorrelation. How is it the numerical computation of the autocorrelation? Now, remember, the autocorrelation, you know, in formulas is this. So it is R, how did I call it? X, right? X, right? Okay. So Rxxk is equal to the expectation of xn plus n plus k. Okay? Now, you know, if I have these data, you know, since these data are generated as they are, so I cannot calculate the expectation. Because I generate as a Gaussian, you know, they might be correlated in some way. So, I cannot have the expectation. So how to compute the sample autocorrelation? So the sample means for the data that I have. Okay? For the sample autocorrelation, it's computed this way. So I sum on all the data that I have, okay, of what? Of xn plus k. And then everything is divided by the number of samples. So n number of samples is 1,000, right? Okay. So this one number is 1,000. And the number index n goes from 1 to 1,000. Okay? So, now this is the sample autocorrelation. So that one is my best estimate of the autocorrelation. Okay? Fine. So, you know, luckily, MATLAB has a built-in way to compute the autocorrelation. Okay? So, you know, it's, let's see, it's hard. Okay? It is a correlation sequence. Huh? So, returns a correlation, blah, blah. And now it's X-core. Okay, X-core, you know, it says, if I have a sequence A and another sequence B, okay, and it's a cross correlation between the sequence A and the sequence B. Now, if they have the same length, it is 2n minus 1. Okay, well, let's make it. So we have a GRXX is equal to X-core of X with itself. Okay? So, you know, we have this, and then let's plot it. Let's see how it is. So, you know, let's start with making some plots. So, if I make a plot of X and a power pose of 10 seconds, okay? And then in this way, you know, I can show how we use this random sequence. Okay, this is the sequence 1000. Okay? These are the randomly generated sequence. Then I have a roots. I can make a pause of 10 seconds. And then I have a cross correlation, and then I make a plot of R x-axis. Now you know, let's look at the cross correlation. I haven't calculated yet. This is 10 seconds. This 10 seconds is taking more. I remove a pose, I don't know. Sometimes it creates trouble. Okay, this is the autocorrelation. Now we know that that one is a white noise because I generated randomly. So I mean the theory says that if it is a white noise, this one is a sigma squared x time delta k. But you know, in practice, things have a limited set, and I cannot expect this one to be a perfectly ideal autocorrelation. And that's the behavior. So the autocorrelation has a delta at the center. So don't forget, the time axis, the index here of the time, is going between minus, 0 is the center, and that is plus. Okay? So because of the way you computed the autocorrelation, the 0 is in the center. Now what I want to do now is the following. I want to compare the position of the roots when I have a sequence of 1,000 samples, when just computing the sequence, and the position of the roots for the cross correlation, for the autocorrelation. Okay? So what do I expect by the roots of the autocorrelation? I expect that since when I compute the autocorrelation, I compute B, Z, B star, but you know it's real, so 1 over Z. If this one are some roots, this one has a roots which is a symmetric, conjugate symmetric with respect to the unit circle. So I expect to see a set of roots such that every time I have a roots, 0, I have another one there. Every time I have a root here, I have another here. So they go in pair, okay? So now let's see if 1,000 probably is too much to see this effect, okay? So let me reduce a little bit to 100. Okay? And so let me now compute the roots of R x-axis. Okay? And let's see how they behave. Here it is. The 100 is shorter, okay? So we can see that, you know, every time there is a root inside a 0, there is a 0 outside in a symmetric position, okay? Every time I have 0, another 0. Every time I have 0, another 0. 0, 0. You know, this, 0, 0. Inside, outside. If I zoom it, I can see inside, outside, inside, outside, inside, outside, inside, outside. Okay? So this is what I wanted to show you. And this probably is more convincing than writing so many equations. Okay? So every time you have an autocorrelation sequence, this autocorrelation sequence, okay, has roots that are inside and outside. You know, and if I just, and now let me go to where I wanted to go. So if now I want to extract the minimum phase sequence corresponding to the same original one, what should I do? I just need to pick up these are 0, this, I don't know, here is faster, this. All the zeros inside. So by picking up all the 0, I get the limit. So I get a new sequence which is big min, which is the minimum phase equivalent of that. And all the roots outside are the maximum phase. It is done in this way, no question of that. Okay? And you know, and it makes no sense to make a trick with a sequence with 3 numbers. Because you know the practical sequence are 1000, as you know it was suggesting, 100, 3000, 500,000. Ma mi ha detto che avevo preso quest'aula fino alle 7 di la verità. Non c'è nessun problema perché oggi finisco adesso.
No, però mi hanno scusi, a me hanno detto che sono 4. Io al massimo mi dispiace.
Chiudiamo. Però io avevo chiesto, diciamo,
Adesso chiedo.
ai servizi generali di averla fino alle 7.
Sì, ma non.
No, perché oggi devo prendere un aereo e non fa niente, perché sennò teniamo fino alle 7. Assolutamente, dopo sento mai dopo, grazie. Ok, so I was closing, so no issue. Huh? So that's, I mean, this is just to show you in a more convincing way, you know, that's this phenomenon, okay? So beyond the equation, keep in mind that, and the way to build it is exactly this way. So you put the root, select the roots inside, build the minimum phase in this way. If the roots are the denominator, those roots are pole, you select the poles go, you know, inside the circle, those are the minimum phase, and so on. Thanks for this. You have a code.